Right now, we are at gas laws, the experimental basis. We're actually going to do this in two parts. We'll do part one, then we'll go to the ideal gas law, then we'll do part two. Part two, we'll be doing problems based on the gas laws. And there are 5 gas laws to know how to use. So let's do the introduction first, then the ideal gas law, then back to this. All right, so gas laws, the experimental basis. We want to understand the basis of the gas laws, Boyle's law, Charles' law, Avogadro's hypothesis. There's also Gay-Lussac's law, and there's the combined gas law. All right, and we want to know how to use those laws, and that's going to be the second part. So there are 4 fundamental properties of gases that we want to understand and know how to use. One is pressure. The uppercase P is the variable we use for that, and it's measured in atmospheres or millimeters of mercury. We've already been introduced to that. Another one is volume. We use an uppercase V for that, and it's measured in liters. Another thing we want to know is the amount of molecules, the amount of gas molecules. That means how many. We use the letter N to denote that, and it's measured in moles. And finally, we want to know the temperature of the gas molecules. So we use the uppercase T to represent that, and it's always measured in Kelvin. You can see I've wrote Celsius here and crossed it out to make sure you understand that when we use the gas laws, we always use Kelvin. All right, so what we're going to do here is we're going to take a look at Boyle's law. Boyle's law is the relationship between pressure and volume. And oftentimes in a science, when you're studying something like 4 properties, what you want to do is you want to constrain 2 of them, meaning make sure they don't change, and just allow 2 to interact to see how they interact. Maybe there's no interaction. Maybe there is. So in Boyle's law, we keep the moles of gas the same and the temperature the same. And we want to see the relationship between pressure and volume. So here I've drawn a container, what I consider to be a large container compared to this one on the right. And in this large container, we've got 9 molecules of gas. And we're going to take this gas and we're going to squeeze the container down to a smaller size. And so that's why we have V2 here. V1 is the initial volume, V2 is the final volume. You can see that it's definitely changed. We want to see if the pressure stays the same or if it changes. So let's take a look at a video where we can see this. So as you can see in this video, this is a Boyle's law apparatus. And you should be able to see a green circle. That is a pressure gauge that measures things in pounds per square inch. It is hooked by a rigid tube to a syringe. And what we're going to do here with this is we're going to take this syringe, which is airtight, and we're going to push the plunger into the syringe and decrease the volume in the syringe and see what happens to the pressure of the gas. So we're going to change the volume and see what happens to the pressure. So let's take a look here. Now, as you can see, our initial volume is at 35 milliliters of gas. We're going to ignore the gas in the tube and the gas inside of the pressure gauge. So we're just going to look at what's inside of the syringe. And it starts at 15 psi, and now there it is at 16.5 psi. And the volume is 30. We change the volume to 25, and we look at the pressure, and now it's at 19. We change the volume to 20 milliliters of gas left in the syringe. And we see that the pressure is what looks like 22.5 psi. All right. So we have seen that when we decrease the volume, the pressure does increase. So let's take a look at how we would understand that and how we would figure out what's going on. So I'm going to go back to my Elmo. And you have just seen that we have changed the volume, and we've seen that the pressure does indeed change from what we saw in the video. So these are the numbers that you can read from the video. The initial volume was 35 milliliters, and the pressure was 15.0 psi. When we decreased the volume to 30 milliliters, the pressure increased to 16.5 psi. And when we decreased the volume yet again by 5 milliliters, the pressure increased to 19. And then finally, we decreased the volume to 20 and the pressure increased again. If you look at these pressure increases, the first increase was 1.5. The second increase was 2.5, and the third increase was 3.5. The increases in pressure don't match the decrease in volume. So when we plot this, we can see that if I put pressure on the y-axis and volume on the x-axis and plot these points, you can see that we get a curve here and not a straight line. The important thing about this curve is we can see that as the volume increases, the pressure decreases. Okay, so this is an indication of what's called an inverse relationship. And so to confirm that this is an inverse relationship, what we want to do is, in this case, we'll keep the pressure the same, but we're going to make a table of 1 over the volume. So we're going to take 35 and divide it into 1. We're going to take 30 and divide it into 1, and so forth. When we do that, we get a new table. And this is what the new table looks like. So this number here, 0.029, is 1 divided by 35. This is 1 divided by 30, 1 divided by 25, and 1 divided by 20. And these are the pressures. They have not changed. Now, when we plot these points, so 1 over the volume versus the pressure, we see that we get a pretty nice straight line. Not perfectly, but this is an experiment, so we're not going to get perfection. But that's a pretty linear line. Now, you can see that I didn't really expand this enough to show you everything, but I wanted to go from 0 to 0.06. Notice the pressure starts at 15. I plotted this again where this is 0, 0, and let's take a look at what we get. Now, when we plot these again, where we have a 0, 0, so this is 0 right here, you'll notice that I can extrapolate back from these 4 points, which still form a straight line, and they extrapolate back here to about 4 psi. Now, this should extrapolate back to 0, 0, which is proof of anything that we didn't do that great of a job. But also maybe we should not have ignored the gas inside of the gauge or the gas inside of the tube. But nonetheless, we can still see that that's linear. And I think it makes sense that if there is no pressure, there should be 0 volume. Or if you have no volume, no pressure, so to speak. Or I should say 1 over the volume, not the other way around. Okay, so here's the graph. All right, so let's take a look at what we can learn from this graph. So here I've drawn the graph again. Here's the pressure, here's 1 over V, and it's a straight line. So this means that since we have a straight line here, that the pressure is proportional to 1 over V. Now we can get rid of this proportionality symbol and put equal there and say that the pressure is equal to kV over V, where kV is the volume constant for gases. Okay, so here's the graph again. P and 1 over V, a straight line, and I've drawn 2 points on the line. So at point 1, you've got pressure 1. And at point 1, you've got 1 over V1. So here you could write P1 is equal to KV over V1. And at point 2, you can do the same thing. P2 is equal to KV over V2. Now I'm going to take this first equation and solve for KV. That simply means I'm going to get KV on one side of the equation, everything else on the other side. And I get P1 times V1 is equal to KV, or I should say K sub V. And I do the same thing for the second equation. I get P2V2 is equal to K sub V. So here, if P1V1 is K sub V and P2V2 is K sub V, that means that P1V1 is equal to P2V2, and this is Boyle's law. So we've arrived at Boyle's law by doing a little experiment. Let's take a look at someone else's law. So this is Gay-Lussac's law, where we're going to look at the relationship between pressure and temperature. And so here the moles and volume are constant. So remember, moles are N and volume is V. So how do we make sure that the moles don't change and the volume doesn't change? Well, in this experiment, we're going to use a steel sphere. And because it's a steel sphere, its volume cannot change. And to change the temperature of the steel sphere, we're going to use cold water and we're going to use hot water. So we're going to put the sphere in cold water. And because of thermal equilibrium, the gas in the sphere should become the same temperature as the sphere, which should become the same temperature as the cold water. When we put the sphere into the hot water, the sphere should warm up. The gas inside the sphere should warm up. And because of thermal equilibrium, the gas inside the sphere will become the same temperature as the sphere, which is the same temp as the water. So let's take a look at this video. Okay, here we go. I'm going to close this one. And we're going to look at this. So this is the Gay-Lussac's demo. Here you can see that the sphere is inside the cold water. You can't tell that it's cold water. It's hooked up by this tubing to the gas gauge. This is a jar of tahini that I keep in the freezer so it doesn't go bad. And so it's frozen, and it's put in a pot of water along with this steel sphere. And this is a thermometer. So what we're going to do here is we're going to measure the temperature of the cold water. The sphere has been sitting in there for a while, so it should be about the same temp as the cold water. Then we'll transfer the sphere to hot water. We'll measure the temperature of the hot water. And in both instances, we'll look at the pressure at the cold temp and at the hot temp. So let's take a look at the video. So that shows you that the tubing is still hooked up to the gas gauge. You can see by the reflection, I'm filming this with my phone. And you can see that the temperature is pretty cold. It's 11 degrees Celsius. Not freezing, but 11 degrees Celsius. So that's the temperature of the sphere. Now you can see that this water is steaming. And you can see the temperature rising, and you can see the lens fogging up on my phone. So I have to move the phone off to the side so that the lens will become fog-free. And then we can look at the thermometer and see what the temperature is when we're done. And you can see it's at 87 degrees Celsius. Now let's take a look at what happens when we put the cold sphere into the hot water bath. So it's hard to tell, but the the initial pressure was 15, and now you can see it's increasing. So the pressure is increasing and increasing and increasing, and I'm trying to submerge the steel sphere as best I can into that pot. And you can see that it's climbing a little bit more, and it tops out at about 18.5 psi at that 87 degrees. Now, honestly, since the sphere is cold, the water is probably no longer 87 degrees. It might be a little lower. And then we put the sphere back in the cold water. What happens to the pressure? You can see that the pressure starts dropping. Let me see if I can back this video up to the beginning. And so the cold water, the ice. And if we take a look at the gauge, you can see that it begins at 15. All right, so let's take a look at this data and see what we can do with it. So I'm going to pause this. I'm going to change my share back to the Elmo. Okay, so Gay-Lussac's law, pressure and temp. It's hard for me to draw a little picture where it shows that we're changing the temp and the pressure. So I guess we could do that. We could draw the sphere and all that, but I'm not going to bother with that. So here's the data that we got. So when there was a temperature of 11 degrees Celsius, the pressure was 15.0 atmospheres. And when the temperature was 87, it might have been a little lower than that. We get 18.5 atmospheres. So these are the 2 points plotted up above. And you'll notice I've left all of this here, which we didn't have any data, but I wanted to go back to find out where would the pressure be 0. Now, if I plot this and draw a line straight through, this ends up hitting my graph at about negative 315 degrees Celsius. Now, remember, this temperature here probably wasn't 87. It probably was a little lower because the steel sphere cooled down the water a little bit. So this point should be a little lower, effectively making my line hit the y-axis a little higher. Well, where should that hit the y-axis? And the answer is minus 273.15 degrees Celsius. And so that means because you can't have a pressure lower than 0, that means the lowest temperature you can ever have is minus 273.15 degrees Celsius. So if you can have a lowest temperature and you want to invent a new scale, what scale do you invent? You invent a scale that has the lowest temperature as absolute 0. And absolute 0, you're going to put, you're going to make that 0, and you call that the Kelvin scale. Okay, so let's take a look and see what we can do with this data and figure out what Gay-Lussac's law is. So the important thing here is we got this nice straight line, and the temperature is proportional to the pressure, or we could say the pressure is proportional to the temp. So here we have the temperature and the pressure, and they are directly proportional. So I have the pressure is proportional to the temp. So here, this means that the pressure is equal to KT times the temp, where KT is the temperature proportionality constant. So if I look at a point on this line, we can say that that's P1 and T1, and therefore P1 is equal to KT T1. If I look at another point on this line, point number 2, I can say P2 is equal to KT T2. If I solve both of these for KT, I get P1 over T1 is equal to KT, and I get P2 over T2 is equal to KT, and therefore P1 over T1 is equal to P2 over T2, and this is Gay-Lussac's law. So with these 4 variables, we can get 4 different laws, plus we can do combinations of more than 2. So let's take a look at all the different proportionality laws that we have for this one short section. Now, you don't want to memorize any of these. Here they are. There's Charles' law, which we showed you. Actually, I think we did not show you this one. We did not show you volume and temp, but we showed you Gay-Lussac's law. We showed you Boyle's law. I did not show you a combined gas law video, nor did I show you Avogadro's hypothesis. But these are the 5 equations. And boy, I tell you, for a chapter like this, I don't want to memorize 5 equations. Well, if you tune in for the second part of this section, I will show you how you can use the right law every time without knowing the name of the law. All you have to do is be able to read the information and decide what changes and what does not. All right, thank you for tuning in.